Each week, when we set off to do this show, we start with one core idea. We want to tell you what is new in space and astronomy, and try to remember that Earth is a planet too. When we select stories, we try to find the ones that we're excited to talk about over coffee, or the ones we know we're going to be sharing randomly with strangers who make the mistake of asking, what do astronomers do? We are here, week after week, to inflict space on others. And I hope that when we do, you will return the favor and inflict this show on others. Before I get busy talking about alien planets, the search for fossil life, and the life and death of our universe's very first stars, I want to remind you we have a podcast. On your next road trip, fill the boring scenery with descriptions of the universe beyond our skies and help us in our goal of leaving no mind unscienced. Together, we can make this a summer of astronomy podcast listening. This is Escape Velocity Space News. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. One of the most exciting parts of modern astronomy is the search for life beyond Earth. This search takes so many forms, from looking for worlds beyond Earth to looking for worlds with the stuff of life right here in our solar system. And to me, the most remarkable part of this is the diversity of options we have to explore. Take, for instance, Enceladus. This 300 some odd mile across moon is rocky in the center, icy on the surface, and contains a salty ocean in between. From massive tiger stripes across its surface, scientists have observed the eruption of massive geysers. In 2008, the Cassini mission was able to fly through one of these eruptions and capture samples showing organics, molecules rich in carbon atoms. From its perspective orbiting Saturn, Cassini observed geysers stretching hundreds of miles from the surface. But it turns out Cassini was in the wrong place to capture just how big these geysers can be. JWST, from its location out beyond the moon's orbit, can really see the space around Enceladus and capture the full extent of what Enceladus is able to do. In recent observations, JWST observed geysers stretching more than 6,000 miles. This work is described in a new paper in Nature Astronomy, led by Guillermo Villanova. To push out this far, the geysers need to push out 79 gallons of water per second, or an Olympic swimming pool of water every couple of hours. This was not an expected discovery. As Villanova puts it, quote, "When I was looking at the data, at first, I was thinking I had to be wrong. It was just so shocking to detect a water plume more than 20 times the size of the moon." End quote. There are so many scientifically awesome things about this that I don't fully know where to start. For instance, these geysers are constantly adding water to this world's surroundings. Enceladus orbits in Saturn's ring system in the E ring. This is Saturn's thickest ring, and this new work indicates that 30% of the geyser's water is feeding into the ring. In 2017, Cassini's mission came to an end. Until a new mission can be sent out, JWST will be monitoring just what Enceladus is doing, and its objects will inform future exploration that just might be looking for life. These geysers offer researchers the chance to collect water from Enceladus's oceans without having to dig through the oceans. While Cassini was able to capture samples, it didn't have the kind of instrumentation on board that was needed to look for life. But the next mission should, and now we know it will have 79 gallons a second to sample and explore. Organic molecules are one of those things we have known are out between the stars for several decades. But it has been a challenge to find them at large distances, from not giving off a lot of light to not existing in huge quantities. These large molecules haven't exactly been calling attention to their locations. And this has left us asking, just when did organic molecules start to exist in quantities sufficient to build planets, exosystems, and life forms like us? And now, an answer may be on the way. The JWST was recently pointed at the Gravitationally Lens System, SPT 0418-47. Discovered by the South Pole Telescope, this is two systems perfectly aligned in the sky. The gravity of the nearer galaxy is able to bend the distant system's light around it, creating a bright ring. This gravitational lensing allows us to see a system that would otherwise be too far away and too faint to be captured even with our largest telescopes. The light from SPT 0418-47 has been traveling toward us for 12 billion years. Our universe was just 1.5 billion years old when this light started its journey. And in this light, JWST has discovered organic molecules. This distant galaxy is shrouded in dust and rich in molecules with extremely long carbon chains. Some of these molecules are polycyclic aromatic hydrocarbons, a kind of molecule we see here on Earth in the exhaust of combustion engines and in soot from fires. The presence of both organic molecules and heavy atoms makes it clear that when the universe was just 10% of its present age, multiple generations of stars had already had a chance to live and die and had recycled their atoms to build their surroundings. Commenting on this research, collaborator Joaquin Vieira says, quote, "We didn't expect this. Detecting these complex organic molecules at such a vast distance is game-changing regarding future observations. This work is just the first step, and we're just now learning how to use it and learn its capabilities. We are very excited to see how this plays out." End quote. It just might be that the stuff of planets and life has been part of our universe for the vast majority of its existence. This discovery fills us with hope that life will be out there among the stars. But hope there is life is not the same thing as certainty there is life. And the existence of life on other worlds doesn't mean the existence of intelligent and technologically advanced societies. To get to societies like those on Earth, you need a long period of geological stability on a world with an orbit that remains constant enough to let life evolve to fill the environment. It is currently unclear if systems of long-term stability are the norm or an exception. A lot of the systems we've found have massive planets, the size of Jupiter and larger, that are orbiting right beside their suns. They are called hot Jupiters because in some cases they are heated so much that their atmospheres are getting blown away. These objects weren't something we ever expected, And in trying to explain them, researchers realized that in some solar systems, massive planets are able to spiral in toward their sun, violently destroying most everything else along the way. It was thought that maybe, just maybe, these hot Jupiters always lived alone. And now that theory has been tested. In a new paper in the Astronomical Journal, researchers led by Donghyang Wu reviewed systems containing hot Jupiters and their warmer cousins, and they wanted to see just how many of these systems had one world or had worlds with companions. It turns out the solar systems with Jupiter-like worlds on orbits that were only 10 days or less had detectable companions just 12% of the time. Systems where the Jupiters were a bit further out, with orbits between 10 and 300 days, had companions much more often, with 70% of the hot Jupiters having companions. According to co-author Song-Hyu Wang, quote, "Our research shows that at least a fraction of hot Jupiters cannot form through a violent process," end quote. As JWST is able to explore more and more of these systems, hopefully we'll go from understanding where worlds are to understanding what their atmospheres are made of. But those are stories for another day. For now, we need to go to break, and when we come back, we're going to be looking at how the early universe got started. Stay tuned. Carl Sagan famously said that to make an apple pie, you first have to build a universe. And that raises the question, how do you build a universe? We have a really good understanding of how things went from time equals 0 to about 400,000 years after the Big Bang. We also understand, because we can see it, how things went from a few billion years after the Big Bang to now. What is missing is the time in between, and the still new JWST is being used to rapidly fill in the gaps in our understanding. With 32 dedicated days of observing time, the JWST Advanced Deep Extragalactic Survey is focusing on the first 600 million years of the universe and the stars forming in the first galaxies. This particular epoch is when stars lit up the universe for the first time and turned the opaque clouds of neutral gas transparent. According to observer Kevin Hainline, quote, "Previously, the earliest galaxies we could see just looked like little smudges. And yet those smudges represent millions or even billions of stars at the beginning of the universe. Now we can see that some of them are actually extended objects with visible structure. We can see groupings of stars being born only a few 100 million years after the beginning of time." End quote. The survey has now shown star formation started in fits and starts. It turns out that our early universe was a lot like a campfire that bursts with heat and then fades until someone throws on a new log that refuels the flame. This analogy doesn't just match the way the star formation fizzles and flares, it also matches the reasons. These galaxies are pulling in clouds of gas from their surroundings, and those clouds are able to refuel the star formation just as logs refuel the fire. But this straightforward story may be a little too simplistic. Just as infalling material can fuel new stars, exploding stars can push away material and damp down star formation. As survey co-lead Marcia Reiki put it, quote, "We're finding star formation in the early universe is much more complicated than we thought," end quote. The first stars weren't like anything we see in our modern universe. After the Big Bang, our universe was made of hydrogen, helium, and just a tiny bit of lithium and beryllium. All the heavy atoms our world is built from, and we are built with, were formed in the first generation of stars and in all the stars that formed and died afterward. When stars don't have larger atoms, they can't as effectively radiate away heat. Those first stars grew huge, 140 solar masses and larger, and they burned fast. We still haven't seen any shining, but from computer models, we know what kinds of elements and in what amounts those elements should have been formed. And we have long known that the first stars to form from the first stars should still be out there, somewhere in the mix, being the second generation of stars, and just waiting to be found. While giant stars may only live for millions of years, medium-sized stars can live for billions of years, while the smallest stars may even live for trillions of years. As much as we might want to check the composition of every single star to ask, are you from the mythical second generation of stars? We just haven't had the needed instrumentation until now. Starting observations in 2008, China's Large Sky Area Multi-Object Fiber Spectroscopic Telescope, or LMOST, is showing what is possible with a telescope designed for this kind of a challenge. One of the myriad stars it highlighted was LMOST J101051.9 plus 235850.2. Located about 3,000 miles away, this star has 100 times less sodium and iron than our own sun. Follow-up observations of this star with the Subaru telescope were able to precisely measure the details in the star's composition. Comparison between this star's composition and various supernova models uniquely matched this star and the kinds of supernova that occurred with the first stars. These results are published in the journal Nature and led by Qin-Fan Xing. The way stars die shapes not just the next generation of stars, but also the literal shape of space as they radiate away gravitational waves. These waves are able to compress and expand space in ways that we can, in some cases, actually detect with systems like the LIGO and Virgo gravitational wave detectors. Right now, we can detect gravitational waves from asymmetric explosions like the merger of two black holes, but we can't see symmetric explosions like supernovae. This limitation has researchers asking, what other kinds of objects might we be able to see because they radiate gravitational waves asymmetrically? One researcher, Ore Gottlieb, decided to see if the disks of material around newly formed black holes might be detectable. But along the way to trying to figure that out, he found something else instead. When the star explodes, its jets drill through this material. As Gottlieb explains, quote, a jet starts deep inside of a star and then drills its way out to escape. It's like when you drill a hole into a wall. The spinning drill bit hits the wall and debris spills out of the wall. The drill bit gives that material energy. Similarly, the jets punch through the star, causing the star's material to heat up and spill out. This debris forms the hot layers of a cocoon. End quote. According to Gottlieb, these jets and surrounding cocoons should be a source of gravitational waves, and because this system isn't spherical, these should be detectable sources of gravitational waves after the next upgrade to LIGO. This simulation's results were presented at the American Astronomical Society meeting as a call to action. By making sure folks know what to look for, there is a chance this effect will be spotted earlier. The detection of gravitational waves has pushed technology in ways that are really quite amazing. As I said, these waves contract and expand reality. The thing is, these effects are super tiny, and researchers have had to learn how to measure atom-sized changes in kilometers-long separated mirrors in detectors. These systems are so precise that quantum motions in the mirrors limit what we can detect. To improve our systems, all sources of noise have to be reduced. And this means we even have to worry about things like atoms move faster when they're warm. This leads to thermal noise. While it's possible to cool things, this can create vibrations, obstruct the ability of mirrors to be used as mirrors, or otherwise just make things difficult. Instead, researchers have been working to create materials that can prevent thermal noise in other ways. In the journal Optica, researchers led by Carlos Garcia Nunez describe a new mirror coating they've innovated. This coating can suppress thermal noise and increase sensitivity, hopefully allowing us to see more diverse kinds of gravitational waves, including potentially the ones Gottlieb simulated. It is unknown when these new technologies will be put into action, but I'm still excited to know new improvements will soon be possible. After another break, we're going to journey back to Earth and look back at questions of life once again and learn about newly discovered fossils indicating Earth's first life was found in a way I totally didn't expect. Stay tuned. A few years ago, people started regularly asking, "Do you think you'd ever go to space?" When I was young, I dreamed of being an astronaut, but I had a couple of bad sports injuries that ruled that dream right out. Today, with the rise of space tourism and plans for full-time settlements on both the moon and Mars, it is possible to imagine anyone one day being able to not just fly above the atmosphere, but also walk on alien vistas. No selection to the astronaut corps required. And with this question and these possibilities, I found myself thinking, someday I want to go fossil hunting on Mars. And in today's closer look, we're going to pause and look at our world's past, most primitive life and just what we might one day be able to find on Mars. Let's start with a brief primer on life. Basically, 3 things are needed. Life needs a source of energy that can drive chemical reactions. Sunlight or thermal vent both work. Life needs a solvent that can break down molecules and make reactions easier, something like water. And life needs the nutrients that feed into the reactions and can be used to build up the literal bodies of life forms. At the most simplistic level, life can be broken apart into single-celled life that has no internal membranes, and single-cell and larger life forms that do have membranes. No membranes means no nucleus, means life that is basically a drop of fluid with DNA. These kinds of life forms include bacteria and blue-green algae. When you think of life in clouds or moisture in droplets, you're thinking of prokaryotic, simple-celled life. And we can detect prokaryotic cells in rocks going back 3.4 to 3.5 billion years. And 3.4 to 3.5 billion years ago, several worlds, Mars, Venus, and Earth, all had oceans and may have all had life. On Mars, there was a temporary atmosphere and heat from a variety of sources, including both volcanism and heat from asteroids crashing into the world. On Venus, according to computer models, the atmosphere hadn't yet collapsed into the acidic greenhouse cloud cover of today, and it too had oceans, volcanoes, and impacts. And Earth, not to be left out, was also experiencing all those things. Exactly how long the conditions for life could have lasted on Mars and Venus is still up for debate. But it's thought water existed at least as recently as 2 billion years ago on Mars, and maybe even as recently as 700 million years ago on Venus. And in the grand scheme of extinctions and evolution, these numbers have me thinking. On Earth, just 1.64 billion years ago, we now know that complex cells, those eukaryotes with internal membranes, they had started to form. And we know that thanks to some of the weirdest paleontology I've read to date. In a new paper in the journal Nature, researchers led by Joaquin Brooks first figure out what fossilized lipid molecules look like, and then they go looking for those fossils. Lipids are the chemicals that make up a lot of membranes and include substances like cholesterol, glycerides, and other fatty molecules. They also did the same experiment with steroids. It turns out that while eukaryotes, in all their squishy realness, may be hard to find fossilized, the chemicals that make their cell structures can be found fossilized in some of the Earth's oldest rocks. As Brooks explains, quote, scientists had overlooked these molecules for 4 decades because they do not conform to typical molecular search images, end quote. In this paper, they examined samples from the Barney Creek Formation in Australia that dates back to 1.64 billion years ago. In these ancient rocks, they find what appear to be fossilized materials that say eukaryotic cells already existed when these rocks formed. And this is the kind of result that beautifully matches expectations. From evolutionary models, it was predicted that the first eukaryotic cell to reproduce and become an ancestor to modern cells did that reproducing 1.2 to 1.8 billion years ago. We may just be seeing the fats and steroids that formed in the very first complex cells. Brooks adds, quote, once we knew what we were looking for, we discovered that dozens of other rocks taken from billion-year-old waterways across the world were also oozing with similar fossil molecules, end quote. One of the coolest parts of this discovery is these complex cells fundamentally changed what life was up to. While simple cells generally just sort of exist off whatever they can find, complex cells can start to develop ways to move and to actively hunt down food. As Brooks says, quote, we believe they may have been the first predators on Earth hunting and devouring bacteria, end quote. Life found a way. And then a couple billion years later, life found a way to eat life. And here's the thing. If there were complex cells on Earth 1.64 billion years ago, there could have been complex cells on Mars and Venus. Given Venus's spacecraft-destroying nature, I don't see a great future for paleontology there. But Mars, it's the perfect place to go looking for old rocks. And it just might be that the work done on Earth can one day be repeated on the red planet. There are many, myself included, who have long hoped to explore for possible signs of fossilized simple-celled life on Mars. Here on Earth, we see built up and fossilized bacteria mats called stromatolites. We can both watch new ones form from layers of cyanobacteria, a red-brown algae, and study fossilized stromatolites that date back 3 billion years. This ability to see them form today and compare them to ancient fossils makes it clear that we know what we're seeing. On Mars, we don't have the same laboratory equipment for slicing rocks and examining them at the highest magnifications. But at the level of taking images, there are round structures on Mars that look like they could be stromatolites, and there are researchers arguing that they are stromatolites. As Carl Sagan so eloquently put it, extraordinary claims require extraordinary evidence. All because something looks like a fossilized mat of bacteria in a photo doesn't mean it will look like one under a microscope. And I am not ready to say there are fossilized, simple celled bacteria on Mars. But I'm here to say there could be. And to say that we now know how to also look for the lipids and steroids associated with complex cells. This could happen in our lifetime. I'd love to be an old lady with a high level of cholesterol fossilized in my rocks. Now, I just need to get to Mars with a massive laboratory. Goals. We all need to have them. After the break, we're going to look back at recent launches, landings, and more. Stay tuned. In today's tech news, I'd like to talk about the Parker Solar Probe and its continuing journey to explore where no one has gone before. This spacecraft measures just 3 foot by 10 foot by 7.5 foot. And while small, it is one of the most rugged things we've flown to space. Since its 2018 launch, this mission has been getting closer and closer to the sun and making periodic dives through the sun's outer atmosphere. The most recent dive took place on June 22nd and reached a distance of just 9.2 million kilometers, or about 30 Earth-Moon distances. While we're still waiting to learn more about what was seen this last week, a new paper published in the journal Nature describes what Parker Solar Probe saw in November 2021 during a similar plunge. During that pass, researchers led by Stuart Bale detected streams of high-energy particles coming from solar coronal holes. This is the first time we've directly observed this source of the solar wind. As we near the next solar max, when the sun is most active, these holes will migrate from near the solar pole to near the sun's equator, where the holes can fire particles toward our world and others. Using these new results, researchers hope they can better predict just how solar winds will get blown our way. With improved solar weather forecasts, we hope to be able to better protect astronauts and spacecraft, as well as the beautiful aurora we can see from here on Earth. Next up, I'm pleased to welcome on aerospace correspondent Eric Mattis with this week's Tales from the Launchpad. Hey, Eric.
Hi, Pamela. On June 4th at 12:20 UTC, a Falcon 9 sent another batch of Starlink satellites into orbit from Slick 40 at Cape Canaveral Space Force Station in Florida. Like most Starlink launches, it was relatively uneventful, with the booster successfully landing on the autonomous drone ship Just Read the Instructions. On June 5th at 15:47 UTC, SpaceX launched its 28th cargo launch to the International Space Station from Slick 39A at the Kennedy Space Center. The launch was attempted twice before it left the ground. Each of the previous attempts was scrubbed due to weather. The Cargo Dragon docked with the Harmony module on the ISS about 18 hours later at 09:54 UTC on June 6th. On board the commercial resupply service mission, Dragon were 3 CubeSats and a third part of the new roll-out solar arrays for the ISS. It will take 2 spacewalks to install them, one to do some prep work and the other to install the new solar panel. The CubeSats consist of SC Odin, a student-led Earth observation mission developed at Concordia University in Canada and supported by the Canadian Space Agency as part of their Canadian CubeSat project. SC Odin has a couple of instruments on it, including a high-performance CMOS sensor and a secondary payload of RadFET radiation sensor that will monitor the amount of ionizing radiation the spacecraft is exposed to. The second CubeSat is Moonlight, a 3U CubeSat designed by Aerospace Corporation in partnership with Space Systems Command and the Air Force. Its purpose is to advance space cybersecurity by providing the national security space community with the ability to test and learn in real time in orbit. The third CubeSat is another Canadian satellite, this one a joint project between the USST, the University of Saskatchewan, Saskatchewan Polytechnic, and the Canadian Space Agency. It has 3 technical objectives: testing a new type of radiation dosimeter, testing the use of high-concentration melanin as a radiation shield in space, and an Earth imaging camera. The booster successfully landed on a shortfall of gravitas just over 9 minutes after launch. The next launch this week was the Kinetic 1 Flight 2 mission from the Qiuquan Satellite Launch Center in China, which took place on June 7th. This was the second launch of the Kinetica 1 vehicle, also known as Lijian 1. Manufactured by CAS Space, it is a solid propellant launch vehicle that can lift about 2 tons into low Earth orbit and 1.5 tons into Sun synchronous orbit. On board was a rideshare mission consisting of 26 different satellites, including at least one Earth observation satellite. Like many Chinese launches, we don't have much more information than that at the time that we're recording this episode. A couple of days later, on June 9th, China launched a Kuizhou 1A rocket made by X-Space for the Longjiang 3 mission from the Qiuquan Satellite Launch Center. It carried an experimental communication satellite to low Earth orbit. Wrapping up this week is another rideshare launch, Transporter 8 atop of Falcon 9, launched from Vandenberg Space Force Base in Southern California on June 12th. On board were 72 satellites from various government, commercial, and academic customers, and the usual form factors of individual 3-unit CubeSats, all the way up to larger orbital transfer vehicles, each loaded with dozens of CubeSats. One of the satellites that caught our attention was the Varda W Series 1 in-orbit pharmaceutical production satellite. Producing drugs in space has been a topic of study for decades. According to Varda, with the recent lowering of the costs of satellites and launches, it is now feasible to attempt this as a commercial operation. The satellite bus, the part that provides communication, power, and propulsion, is made by Rocket Lab and is a modified version of their Photon's kick stage. The processing module and re-entry vehicle that will bring the product back to Earth were both manufactured by Varda. The factory on this first mission will operate for 3 months before returning to Earth. There was also another batch of Starlinks launched from Cape Canaveral earlier on the 12th. We keep track of orbital launches by launch site, also called spaceport. According to Rocket Launch Jet Live, so far this year, the US has had 44 launches, China 20, Kazakhstan 5, India 4, New Zealand 3, Japan, Russia each have had 2, and French Guiana, Israel, North Korea, South Korea, and the United Kingdom each have had 1. Of these 85 launches, there have been 5 failures, reminding us that space is hard.
Before we go, we want to remind everyone of a special launch that took place on June 18th, 1983. That launch 40 years ago was the first time NASA let one of their many trained women astronauts fly to space. While the USSR had launched 2 women decades earlier, the U.S. space program took a bit longer, making sure they'd solved all the issues related to a mixed crew and women's health. Quite famously, NASA thought Sally Ride could need as many as 100 tampons for her 6-day journey. Mind you, tampons are sold in boxes of 24 to 30 for a very good reason. Ride also found herself asked more about what makeup she'd be taking than what science she'd be doing. This question is particularly ridiculous since Ride didn't wear makeup. Let's face it, being a woman in science has never been easy, and Ride's challenges played out on national TV. That 1983 launch on the Space Shuttle Challenger was just her first. In 1984, she flew on the Challenger again, this time with Catherine Sullivan. And what would be the first mission to fly 2 women took place. Ride was scheduled to fly again on a latter mission, but after the Challenger disaster, that mission was canceled. Ride, who had a PhD in physics, left the astronaut corps to become a professor, and she also served on the Rogers Commission to investigate the Challenger's explosion. Ride died of pancreatic cancer in 2012. With her death, we all learned that Ride had spent the past 27 years with partner Tam O'Shaughnessy and had been in same-sex relationships throughout much of her adult life. This facet of her had been hidden to allow her to focus on her work. But as she approached death, she made it clear to her partner that her partner could decide how she'd be remembered. Today, during Pride Month, we are now able to say that Ride's launch 40 years ago during Pride was a triumph for more than just women. And that's it for now. Good night, and everyone, remember to go out and look up.